All right, welcome back. Today we're diving headfirst into a really fascinating frontier of pure logic, a place where some questions, just by their very nature, might be completely impossible to solve.
So let's kick things off with a question that sounds super simple, but trust me, it's anything but. Can every single logical problem be solved? I mean, can you always write a program, an algorithm that can tell you if any given statement is universally true? You'd think the answer's got to be yes, right? Well, it turns out the reality is a whole lot stranger. Okay, so before we can even begin to tackle that, we've got to take a step back. We need to explore the world where a question like that even makes sense. And that means we have to challenge something we take for granted every single day: what a sentence actually means. And yeah, believe it or not, this entire mystery really just boils down to that one question. When you say something, what are you really referring to? Is a sentence just a label for true or false? Or is there something deeper going on? Turns out, in the world of logic, there are two big competing schools of thought on this. All right, let's start with the classic answer, the one that's pretty much dominated logic for more than 100 years. It's an elegant, super simple, but also really strict way of seeing things. This idea is called Frege's principle. And honestly, the best way to think about it is like a light switch. Any sentence you can possibly come up with, it's either on, which means it's true, or it's off, meaning it's false. That's it. There is absolutely no dimmer switch, no in between. Every single sentence is just a name for one of those two states, period. And this is where you see the beautiful but kind of weird consequence of Frege's principle. You take these two sentences, the sky is blue and 2 plus 2 equals 4. Both are true, right? So, in a Phrygian world, they mean the exact same thing. They're not about the sky, they're not about numbers. Nope. They both just point to one abstract concept: true. But doesn't that feel a little, I don't know, incomplete? What if two sentences that are both true can still mean fundamentally different things? Well, that thought is exactly what brings us to a more modern, alternative way of thinking. So what's the alternative? Well, it's called non-Fregian logic, and it basically throws out that idea that sentences are just labels for true or false. Instead, it says sentences refer to unique situations or states of affairs. The photography analogy works great here. You can have two totally different photos. They're both true pictures of reality, right? But they capture completely different scenes, so of course they have different meanings. Okay, so a logic built around situations. What does that actually look like under the hood? Let's dive in and see how the machinery works. One of the key examples here is a system called Sentential Calculus with Identity, or much easier, SCI. You can think of it as a formal rulebook for a logic, where, yeah, two sentences can both be true, but they can still have totally different identities or meanings. So, SCI is built on three really elegant rules, or axioms, for what identity means. First one's a gimme. A equals A. A sentence always refers to its own situation. Obvious, right? The second one is about substitution. It says if sentence A and sentence B are describing the exact same situation, then you can swap them out for each other anywhere else and nothing changes. And third, if A and B are the same situation, then they absolutely have to have the same truth value. If one's true, the other must be true. But here's the absolute key. The most important part is what the logic doesn't say. It never says the reverse of that third rule. It never says that just because two sentences are true, they have to be the same situation. And that little omission, that's the firewall. That's what keeps this whole system non-Phrygian and lets the sky is blue and 2 plus 2 equals 4 mean two different things. Okay, so now we've got this really cool, nuanced logic. Let's see what happens when we push it. I mean, what happens when we take this powerful system and just see how far it can go? Because this is where our story takes a really dramatic turn. We're going to give it one more tool: quantifiers. Now, these are the little words that do a ton of heavy lifting in logic. We're talking about words like all, every, some, there exists. Basically, we're about to supercharge this thing. And when we bolt those quantifiers onto our SCI system, we get something new called SCIQ. And this new, souped-up system, it seems so natural, right? But it has a very, very strange property hiding deep inside it. It's undecidable. And that is the big reveal. Undecidable means there is no algorithm, no computer program that you could ever possibly write that can look at any random formula in this SCIQ language and tell you for sure yes or no if it's a universal truth.
The problem of checking for truth in this system is quite literally unsolvable.
And this isn't just a guess, it's been formally proven. SCIQ is undecidable. But you know what? This isn't a weakness. It's actually a sign of incredible power. This system is so expressive, so powerful, that you can use it to describe really complex parts of math, like the rules for groups and rings and fields. We're talking the building blocks of abstract algebra. And it seems that whenever a formal system gets complex enough to talk about things like that, it just inherently creates questions that it can't answer from the inside.
So let's process that for a second. We've built a logical system that, by design, can't solve all of its own problems. So what? What's the big takeaway here? Why does any of this abstract stuff actually matter?
And here's the key idea I want you to walk away with. Undecidability isn't a bug. It's a feature. It's a sign that your system is incredibly expressive. It's so rich that it can talk about really complex ideas. And when you do that, you've basically just bumped up against a fundamental speed limit of the universe for what any formal system is capable of. And that's really why this non-Fregian logic stuff is so important. For logicians, it's like a Rosetta Stone. It gives them a shared framework to compare all kinds of different logics. It lets us crank up the expressive power of other logical systems. But maybe most importantly, it helps us map out the absolute boundaries of what's provable and what's computable. Which leaves us with one last big question to chew on. If a system of pure, formal reason, something we designed to be perfectly consistent, can have questions inside of it that are just fundamentally unanswerable, then what does that say about our own questions? The messy, informal, and infinitely more complex ones we grapple with every single day.